So we are going to start with our applications of your rational equations that you guys started working on last time. You learned how to solve them. So we're going to be practicing solving it. If you still need some practice with that, we're going to get that today. But we're also going to learn situations in which you would use those kinds of equations. So the first kind is our job problems. These kinds of problems, we call them job problems because it usually involves 2 or 3 different people and they're trying to complete some kind of a project. This project, they're trying to mow the lawn, they paint chairs, paint rooms, some kind of project is happening. So we have that Jim can mow the lawn in 2 hours. When Jen mows the lawn, it takes her 3 hours. If they were to work together, how long would it take them to mow the lawn to the nearest minute? And a lot of people, when they see this problem, they're like, oh my gosh, I have absolutely no idea. But I have a formula that's going to make it pretty easy for you. So you want to set it up as their time together over each person's time. So in this problem, it would be over Jim's time first. That would be your first fraction. And then it would be plus, again in the top, time together over Jen's time. And it'll always equal 1 because it's his time plus her time equals 1 whole project. They're always completing 1 whole thing. So it's always equal to a 1. So in this problem, we don't know how long it takes if they work together. So that's what we're trying to find. So my numerator is going to be an x. And then it takes Jim 2 hours, so his fraction would be x over 2. What would be my fraction for Jen? X over 3. We don't know what their time together is. We're trying to figure out how long would it take for them to do it together. Uh-huh.
Oh, never mind.
Okay.
I thought by that you meant like his time plus her time.
No, because he mows the whole lawn in 2 hours.
Oh, okay.
She can mow the whole lawn in 3 hours. But if we work together, because, you know, teamwork makes the dream work, we want to know how long it takes them.
No, I don't want to hear that. No.
So now we have equations just like what you guys had for homework. I'm going to change this to 1 over 1 just so you know I got all 3 of my fractions there. What would be our common denominator? 6. For our first fraction, what would we have to multiply 2 times to make it a 6? 3. So that means I need to multiply my numerator. Also times 3. Need to keep it equivalent. What would we multiply the second one times? 2. So that gives me a 2x. And then the third one times a 6. And now what do we do now that we have common denominators? Cross them out. 3x plus 2x gives us 5x equals 6. Divide by 5, and what do we get? It's going to be a decimal. $1.2. But we want to go back and check the problem. They want it to the nearest minute. So how many minutes do we have in an hour? 60. All of these are talking about hours. Jim was in 2 hours. Jen worked it in 3 hours. Together they can do 1.2 hours. So to turn it into minutes, we just got to multiply times 60. So 1.2 times 60, 72. So they always got to write a sentence. And mow the lawn 72 minutes together. Because it was a word problem, so you need to answer it with a sentence. They ask you in sentences, you answer in sentences. That's called a job. Those people who are like landscapers or they come and they paint your house, construction companies, they actually sit there and figure out how long would it take for this person and this person to work on that job together because they want to do the best job they can and they want to be able to make the most profit that they can. So they deal with this. Not necessarily, because you have to think about it. If they did that, would people keep calling them? No, because word of mouth, especially now with all those websites where you can comment on how the people's jobs were, they're going to say, oh my God, these people are so incredibly slow, and then they'll lose business. So, yes. Okay, next kind of problems we deal with are our DRT problems. This is a formula you've used in science class. We used it a little bit back in 9th grade also. Distance equals rate times time. Does that sound familiar at all? No. Oh no. We're going to use it a lot though. So there are a couple other ways that we can write the same formula. Distance equals rate times time. We can write it so that it's rate equals. But what we have to do is rearrange the formula. I would divide by t here. So that means rate is distance divided by time. Now what if I rewrote it for time to be by itself? What would time equal? Distance divided by rate. Because again, I would go back here. You would divide by the r to get t by itself. So it's distance divided by rate. So it's the same formula, just rewritten in a couple of different ways. We're going to want to use some of those different ways in our equations here. So we have Melissa who walks 3 miles to the house of a friend and then returns home on a bike. She averages 4 miles per hour faster when cycling than when walking, and the total time for both trips is 2 hours. Find her walking speed. So these ones are easier if you set yourself up a little table. Yep. So we're really talking about 2 things here. We're talking about when she's walking to her friend's house and when she's riding the bike. So in the table, we still have distance, rate, and time. So how far away is her friend's house? 3 miles. So whether she's walking or riding the bike that we're just going to assume she borrowed from her friend, it's 3 miles. We don't know. We're just going to assume she borrowed it. So then it says she averages 4 miles per hour faster when cycling than when walking. So I'm going to call her walking rate x, because I don't know how fast she walked yet. So on the bike, it would be x plus 4. It would be her walking speed plus the 4 miles per hour that she goes faster. So then to complete my table, I want to use the little formula that we did up here to rearrange it. For our time, it's distance divided by rate. So distance divided by rate. Same thing with the bike. Distance over rate. So now we got the whole table set up. To get the equation, the total time for both trips is 2 hours. So for her to walk to her friend's house, borrow the bike and come back, total time, 2 hours. So we have to take her time walking, which we said was 3 over x. Add into it her time riding the bike, which was 3 over x plus 4, and it's going to equal 2. Yes, we have have to get a common denominator. So keeping in mind that 2 is over a 1, what would our common denominator be? Danielle? X times x plus 4. Yeah. Because you can't just add a 4 to a denominator. When you're trying to make a common denominator, you can only make it bigger by multiplying. So I can't just add plus 4 to the x to make it x plus 4. I would have to multiply my two denominators together. So our first fraction here, we would have to multiply this times x plus 4. So I would get a numerator of 3x plus 12 when I distribute. What would we multiply the second one times? X. That one gives me a 3x. And then the third one? Third one's just over a 1, so we have to multiply the whole thing times x plus 4. It needs both of them. So it's like I'm distributing the 2x. So I get 2x squared plus 8x. So now that we have a common denominator, what can we do? Cross it out. So 3x plus 3x gives me a 6x plus 12 equals a 2x squared plus 8x. Yes, I do. I want to get everything over on one side so that's equal to a 0. So I subtract my 6x, subtract my 12. I get 0 equals 2x squared plus 2x minus 12. Now what do we have to do? Factor, everybody's favorite thing, factor. So do we have a GCF factor? Yeah, we do. What is it? 2. So it would be 2 times x squared plus x minus 6. Can we factor that again? We sure can. What does that factor into? Will our signs be same or different? Different. 3 and 2. So we want a plus 3 and a minus 2. So now I'd set them equal to 0. So I get an x equals 2, x equals negative 3, and then if I try to set 2 equal to 0, that doesn't work. So can I keep both those answers? You have to think about it. They told us to find her walking speed. Can I have a walking speed of negative 3 miles per hour? No. So that's extraneous. Huh? No, we're moving beyond reject. Yeah. Yep. Extraneous. So her walking speed is 2 miles per hour. Remember, her walking speed was just x. X is 2, so her walking speed is 2 miles an hour. What if they wanted her biking speed? It would be 6 miles per hour. Good. So far, so good? Not too bad? Getting some practice with those equations. All right, let's go to our 2 examples on the back. So you canoe upstream for 20 miles. You turn around, you come downstream for 40 miles. Because of the current, it takes you the same amount of time both ways. In still water, you can paddle at a rate of 6 miles per hour. How fast is the current of the river? Now, my first question is, everybody understands that if you're going against the stream, you don't go as fast as when you go with the stream, right? Okay, good. See, this is when I lost it before. This is when I started thinking about the 8 versus 12. So, no, if you go against the stream, you go slower. What did you ask, Danielle? For what? No, they still have to work harder to go upstream because you're going against the current. I know, because they're weird. Alright, so we have upstream versus downstream. I'm setting up the same kind of chart we had on the front on the last problem we just did. Distance, rate, and time. So how far did we canoe upstream? 20 miles. Downstream, we went 40 miles. So now for our rate, they told us in still water, you can paddle at a rate of 6 miles per hour. But when you're going upstream, you're going against the current of the water. So it's your 6 miles per hour minus the current of the river. It makes you go slower. So you take your speed and you subtract the water speed to figure out your speed. But when you're going downstream, it's going to be 6 plus the current of the river because you're going with the current this time, so it makes you go faster. So you just kind of have to think about it. Okay, which one's going to make me go slower? So if I'm going against the stream, or if they're talking to you about going against the wind, that's going to make you go slower. So you want to subtract the wind speed, or in this case, the water speed. So again, our time would be distance over rate. Distance over rate. So then it tells us because of the current, it takes you the same amount of time both ways. So for our equation this time, we're going to take the times and set them equal to each other because they are the same time upstream and downstream. So then, yeah, that's 6. So now we cross multiply. These are like the first kinds of equations we had in the notes last time. So it's going to be 20 times 6 plus x equals 40 times 6 minus x. I always like to show that step because a lot of people forget to distribute to both terms. Then we want to distribute, so 120 plus 20x equals 240 minus 40x. We want to get our x's together, so I would add my 40, subtract my 120, and what's our last step? Divide by 60, so what does x equal? 2. So we say the current of the river is 2 miles per hour. So then our last kind of problem is a record / mixture kind of problem. I'm sorry, what's up? No. Because if you remember with our rate up here, this is our rate minus the current. And that's what we were trying to find, is what the current was. The current is 2 miles an hour. We were just finding x that time. All right. So back to this problem down here, our mixture problem. Normally the kinds of questions that they ask for this involve, like, you're trying to put together a trail mix and you want it to be 25% almonds and 13% walnuts and like 50% chocolate chips, if it's the way I make it. So then you would have to go and figure out all the different percentages and put it together. Yeah? Definitely don't put any tree nuts in there then. So I changed it around this time, and I was talking about games because I figured that might make it a little bit more sense for you. So far, Anne and Maria play tennis almost every single week. Anne has won 12 out of 20 matches. They want to know how many matches will Anne have to win in order to improve her winning percentage to 75%. So we don't need a box for this one. The way we're going to set this up is the amount of games she has won over the amount of her total matches so far. So far she's won 12 out of 20. We're trying to figure out how many she needs to win in a row to improve her percentage. So we're going to add x to the 12, because we got to figure out how many winning games does she need. But we also need to add the x to the 20, because she's still playing more games. It's not going to still be out of 20. That number goes up also. So her number of winning games goes up, and her number of games total goes up. We're going to set it equal to 75%, but I don't want to use 75%. What's 75% as a fraction? 3/4. That's what I want to use. So now we can cross multiply. So I'm going to have 4 times 12 plus x equals 3 times 20 plus x. I get 48 plus 4x equals 60 plus 3x. So what does x equal? Anybody get it yet? 12. So Anne will have to win 12 games in a row. So once she gets those 12 more games, she's got her 75%.